Welcome. In today's video, we are going to derive an expression for the mean and variance of the Pareto distribution. To begin with, let us first define the probability density function. So suppose x has a Pareto distribution with parameters alpha and lambda. Then the PDF, or the probability density function of x is given by the following. F subscript x of x is equal to alpha lambda to the alpha all over x to the alpha plus 1, where x is greater than or equal to lambda. That is the definition we'll be using today to evaluate this integral, this expectation. So, the expected value of x, which we will now compute now, we are dealing with a continuous random variable, not a discrete random variable, so we will use the continuous definition of expectation, and by definition it is the expected value of x is equal to the integral of x in the support of x multiplied by fx of x dx. In this particular case, the possible values of x are x greater than or equal to lambda, and therefore our terminals on our integral or our integrand are lambda to infinity. And then of course we've got x multiplied by alpha lambda to the alpha all over x to the alpha plus 1 dx. Now, from here what we can notice is that the x at the top here will cancel with the alpha, one of the x's in the denominator, leaving us with x to the alpha. Or, in other words, we can actually rewrite this as lambda to infinity of alpha lambda to the alpha x to the negative alpha dx. And the reason I've written it in that form is because it's easier to we're going to integrate with respect to a power of x. Visualizing it as a power is often easier to integrate. Now, as an aside, before I continue, I just want to point out one notable fact, that of course alpha and lambda are greater than 0 as parameters in order for this to function. So, from here, what we can say is we can integrate with respect to x. We know a power, we know what the rule is for a power. Add 1 to a power, divide by the new power. So let's do that. So if we add 1 to the power, alpha lambda to the alpha, alpha 1 to the alpha, we'd add 1 to the power, so we get x to the negative alpha plus 1, and then we divide that all by negative alpha plus 1, the new power. And then, of course, we're integrating that from lambda to infinity with respect to x. There is one important feature, however, that I haven't mentioned here, is that this power is, or this integral, is only true for when x, or when alpha, is not equal to 1. Because if alpha is equal to 1, you've got x to the negative 1, or 1 over x, and we know when we integrate 1 over x, we get log of x. So this case happens to be true when alpha is not equal to 1. There is a secondary case that we need to be wary of that becomes alpha lambda to the alpha log x from lambda to infinity, of course, where alpha does equal 1. And let's keep that in mind as we go through this problem. So we're actually going to need to evaluate two integrals now. Now, in both of these scenarios, we're dealing with improper integrals. And when we deal with improper integrals, we need to take limits. We need to use limits. So that becomes the limit as L approaches infinity of the function alpha lambda to the alpha on negative alpha plus 1 of x to the negative alpha plus 1 lambda to the L, when of course alpha is not equal to 1, and again the limit as L approaches infinity of alpha lambda to the alpha log of x from lambda to L when alpha is equal to 1. Substituting now our terminals of lambda and L into the equation, we would get the following. So still have our limit as L approaches infinity of alpha lambda to the alpha over negative alpha plus 1, L to the negative alpha plus 1 minus alpha lambda to the alpha over negative alpha plus 1 lambda to the negative alpha plus 1. For the first part of this equation, alpha not equal to the 1. And of course, for the second half of the cases, this would become the limit as L approaches infinity of alpha lambda to the alpha log L minus alpha lambda to the alpha log lambda for the case where alpha is equal to 1. And so far, so good. Now, there is one point to note here. And that point is simply we need to break up this first part, in fact, into two cases. The case where alpha is greater than 1 and the case where alpha is less than 1. So let me do that in this next step. Copy that and paste it down here. And let's give myself a little bit more room. And we're going to take exactly the same case, copy, and we're going to look at it a second time as well. So there'll now be three cases here. There'll be three cases, and the three cases are alpha greater than 1, alpha less than 1, and of course alpha equals 1. Now, for going back to the original step, let's just concentrate first on the alpha is equal to 1. So as L approaches infinity, log of L approaches infinity, and therefore the entire expression here approaches infinity. So I can actually rewrite that bottom term, where the case where alpha is equal to 1, as simply infinity. Not going to muck about here. Now, the other part to note is that the term here that I had up here before, where we had alpha lambda to the alpha, to be clear, the lambda to the alpha here will cancel with the lambda to the negative alpha here, and we're just going to be left with lambda to the power of 1. So I'm not going to I'm going to rewrite the top expressions not as the formula that I've just presented, but rather just lambda here in my split out of the cases. There's no need to complicate it any further. I'm just going to make that simplification in this next step here. All good and all well. So let's have a look at these two cases now. Well, let's have a look at the first case. When alpha is greater than 1, this means that the power here is going to be greater than 1, or sorry, greater than 0. Sorry, just the alpha plus 1 is going to be less than 0. Sorry, let me restate that again. Negative alpha plus 1 will be less than 0 when alpha is greater than 1. Which means our expression here will be L, which is a really big number because it approaches infinity, to the power of a negative. And when we take a really big number to the power of a negative, what we end up with is, of course, a really small number. We end up with 0, in fact. And so this first whole term in the expression disappears to 0, leaving us with the second term here. So then we can write that as negative alpha lambda on negative alpha plus 1 for the first case. For the second case, where alpha is less than 1, negative alpha plus 1 will be a positive number, and therefore we're going to have infinity to a positive number, and infinity to a positive number is, of course, going to be infinity. And so this whole expression here will go to infinity. And so we have the case of infinity where alpha is less than 1, alpha greater than 1, and of course we already had infinity where alpha is equal to 1. And if we wanted to simplify this a little bit further, we could just simplify it down to two cases: infinity where alpha is less than or equal to 1, or alpha lambda on, and if we put this negative out the front through the denominator, we can rewrite that as alpha minus 1 in the denominator for when alpha is greater than 1. And you can see here we have now derived an expression for the expectation, but the definition of expectation, it seems to be only defined for a particular set of alpha. When alpha is less than 1, the expectation does not, or is not well defined. So, now that we've computed the expectation, we can now look at the variance, and we're going to see a similar pattern approach, or similar pattern emerge. So to compute the variance, of course, we need to take the expected value of x squared. By definition, this is the integral of x across the support of x squared fx of x dx. We're going to substitute in our terminals, which are from, again, lambda to infinity, similar to before. X squared multiplied by alpha lambda to the alpha all over x to the alpha plus 1 dx. And in this particular instance, the x squared will cancel with the x to the alpha plus 1. we do that here, the 2 will cancel with the alpha plus 1, leaving alpha minus 1 in the numerator. Or in actuality, what we can rewrite this is, or we can rewrite this as negative lambda to the infinity of alpha lambda to the alpha x to the power of, now alpha minus 1 is in the denominator. If we want to express it in the numerator, it would become minus alpha plus 1 dx. And in a similar expression, or in a similar vein, we could have, we've got to add 1 to the power, divide by the new power. So again, we're going to have the case where we'll have alpha lambda to the alpha on. Now, what's the new power? Well, the new power will be x minus alpha plus 2. And so we've got to divide by a negative alpha plus 2. And then, of course, there's actually another type. There's another expression here that is possible. Similar to as before, notice if alpha is equal to 2. So, by the way, this is the case where alpha doesn't equal 2. When alpha is equal to 2, the power here is negative 2 plus 1, or negative 1. We've got an x to the negative 1, or 1 over x, and when we integrate 1 over x with respect to x, we end up with log of x. So the other term here is alpha lambda to the alpha log of x. And of course, we're going to put in the terminals lambda to infinity, lambda to infinity. So very similar to as before, we have two cases. It's just now our point of reference is not alpha equals 1, but rather alpha equals 2. And in a similar way, what we're going to do is we're going to use our limits, again, because we're dealing with improper integrals involving infinities. So the proper way to do this is to say that is the limit as L approaches infinity of the integral a lambda to the alpha on negative alpha plus 2 x to the negative alpha plus 2 lambda to the L when a alpha does not equal 2, and then the limit as L approaches infinity of the second term, which is alpha lambda to the alpha log of x lambda to the L, alpha is equal to 2. And in a similar vein to as before, what we will do is let's first pull through the integrals, or let's pull through or evaluate the limits, the terminals, I should say. So the limit as L approaches infinity of, so now we're going to substitute our lambda and our L in the terminals. That becomes alpha lambda to the alpha all over negative a alpha plus 2 L to the negative alpha plus 2 minus alpha lambda to the alpha on negative alpha plus 2 times lambda to the negative alpha plus 2, close the brackets, alpha not equal to 2. In a similar expression, we have limit as L approaches infinity of alpha lambda to the alpha log of L for the first part of the terminal minus the second half of the terminal, which would be minus alpha lambda to the alpha log of lambda when alpha is equal to 2. Now, in a similar way to before, the first thing I'm going to notice is that the lambda to the alpha here actually will cancel out with the lambda to the negative alpha here. So we can cancel those two out, and well, maybe I won't cancel it out just like that because it might be a bit confusing, but rather I'm going to cancel it out with the negative alpha out here to denote the fact that I've got still a lambda squared in our expression. And similar to before, what I'm going to do is I'm actually going to split this first part into two cases. The case where alpha is greater than 2 and the case where alpha is less than 2. So if I copy that down and paste it in here, just noting that I'm going to need a new version of the condition. So let's take that, copy it here and paste it up here. So actually we will have 3 versions of the condition. We will have the case where alpha is greater than 2, in the case where alpha is less than 2, in the case where alpha equals 2. And of course I'm just going to simplify the alpha part here for a second. In that we don't want alpha or lambda to the alpha anymore. It becomes lambda squared, as we said before. The other point to note as well with this is to note that when alpha equals 2, we take the limit as, or in the last part of this condition or these cases, the limit as L approaches infinity of log of L is simply infinity. And so this whole term down the bottom, as before in the first case when we're evaluating expectation, simply becomes infinity. And so we can just rewrite that last condition as infinity. And I'll bring out through all these cases here. Let's copy these. Well, we don't need to copy the conditions anymore because this is what we have. As L approaches infinity, and again, this is the case where alpha is greater than 2. If alpha is greater than 2, then negative alpha plus 2 will be less than 0. And if that power is less than 0, when we take infinity to a power less than 0, then we will end up with 0 in this first term. So that whole first term becomes eliminated and is just 0. And therefore, we're only left with the final term here. And so that's what I'm going to rewrite. Negative alpha lambda squared all over negative alpha plus 2. Plus 2 in the parts here. And that is true for alpha greater than or equal to 2. For the second part, where alpha is less than 2, if alpha is less than 2, negative alpha plus 2 will be positive. And when we have infinity to a positive number, what we will get is another infinity. And therefore, this whole expression here will tend towards infinity as L tends towards infinity. And so we have infinity when alpha is less than 2. And of course, as with the last case, we have infinity when alpha is equal to 2. And finally, when we evaluate all of this, or when we can simplify this slightly, we can actually combine the last two cases and just tidy up the first term here by taking that negative out the front and putting it through the denominator. We get alpha lambda squared on alpha minus 2 when alpha is greater than 2, and infinity when alpha is less than or equal to 2. And so again, in a similar fashion to as before, we have two cases. And therefore, finally, after we've evaluated these two cases, we can now take a look at expectation. And remember we can take a look at the variance of x. And by definition, the variance of x is the expected value of x squared minus the expected value of x all squared. Now, in this particular instance, it's going to be a little bit complicated because if you think about it, we actually are adding together two terms, we could say. There were two we're adding cases and we're subtracting cases from it, right? We've got a case here, and then we've actually got a case here for when alpha is less than or equal to 1. For the time being, we're actually to simplify it down a little bit, we're just going to have a look at when the cases overlap. So we know when alpha is greater than 2 and when alpha is less than 2. You'll see what I mean in a sec, because that becomes alpha lambda squared alpha minus 2 minus alpha lambda on alpha minus 1, I believe was the answer above, all squared when alpha is greater than 2. And then when we look at the secondary case, we're just going to end up with an undefined variance when alpha is greater than or equal, less than or equal to 2. Less than or equal to 2. Because that not only covers the first part of the expression, it covers this part here, but it also looks at the case where what happens when alpha is between 1 and 2. Well, we still have this first expression here blowing out to infinity, and therefore we will write infinity, or in this case sort of undefined. Keeping that in mind, what do we have next? So, in the next part of this, we can just simplify. So the cases become lambda alpha squared all over alpha minus 2 minus alpha squared lambda squared on alpha minus 1 all squared when alpha is greater than or equal to 2, and then infinity where alpha is less than or equal to 2. We'll do a bit more simplification. So we need to add the top fractions here. In order to add the top fractions, we need to have the same denominator. To find the same denominator, we need to find the lowest common multiple. The lowest common multiple of alpha minus 2 and alpha minus 1 squared is simply alpha minus 2 alpha minus 1 squared for both of the fractions. So I'm going to write that alpha minus 2 alpha minus 1 squared. Now for the first fraction, in order to go from alpha minus 2 to alpha minus 2 alpha minus 1 squared in the denominator, we needed to multiply by alpha minus 1 squared. So that's what we're going to multiply the numerator by. And similarly, in a similar reasoning, to go from alpha minus 1 squared to alpha minus 2 alpha minus 1 squared in the second fraction, in the denominator of the second fraction, we needed to multiply by alpha minus 2, and then we've still got our alpha squared lambda squared from the numerator before. That gives us alpha greater than 2, and then still infinity for the case where alpha is less than 2. Let's do a little bit of simplification here. Again, we're going to rewrite these fractions. We'll do some expansion. That becomes lambda alpha squared minus 2 alpha plus 1 and in fact we can continue minus alpha minus 2 alpha squared lambda squared over alpha minus 2 alpha minus 1 squared. And this is the case where alpha is greater than 2, or infinity when alpha is less than or equal to 2. Now, in this particular instance here, let's expand the brackets. So this expansion here becomes alpha lambda squared times alpha squared, which gives us alpha cubed lambda squared. Then we've got alpha lambda squared times negative 2 alpha gives us minus 2 alpha squared lambda squared. Then here we have finally a plus 1 times alpha lambda squared, so we've got plus alpha lambda squared here. And the second part of this expression, we've got a minus alpha times alpha squared lambda squared, which gives us minus alpha cubed lambda squared. And then we've got a minus negative 2, so a positive 2 times alpha squared lambda squared. So plus 2 alpha squared lambda squared. And we've got that all over alpha minus 2 alpha minus 1 all squared for the case where alpha is greater than 2, and infinity where alpha is less than or equal to 2. And finally, here in this expression, we notice that the alpha cubed lambda squared will cancel out with the negative alpha cubed lambda squared here. The negative 2 alpha squared lambda squared will cancel out with the positive 2 alpha squared lambda squared here, which only leaves us with the alpha lambda squared in the numerator. And so after all that algebra, we're just left with alpha minus 2, the denominator, or the denominator stays the same, but the numerator simply is alpha lambda squared, close the brackets, alpha greater than 2, or infinity where alpha is less than 2. And there you have it, ladies and gentlemen. We have derived an expression for the variance of x. And for completeness, of course, we can say that the standard deviation of x, which is the square root of the variance of x, well, that will take the following forms. We can say that's the square root of alpha lambda squared on alpha minus 2 alpha minus 1 squared, when of course alpha is greater than 2, or simply still infinity when alpha is less than or equal to 2. So there you have it, ladies and gentlemen. What we have derived here is the expectation and the variance of the Pareto distribution with parameters alpha and lambda. One of the things that we needed to make sure or be careful about is that because we were dealing with integrating with powers, we needed to separate the two cases of when the power that we were integrating by was equal to -1 or L or otherwise, so that we could deal with the two cases of log. And finally, we also needed to consider the cases where after integration, whether the power was negative or positive, so when we take the limit as L approaches infinity, whether that power blows out to infinity or converges to 0. I hope that video was useful. Thank you for watching. I hope to see you in the next one.